For high-throughput enterprise pipelines, the cost of querying public cloud APIs is reaching a point of diminishing returns. At current rates, premium endpoints like GPT 5.5 or Claude 4.7 can charge $30 for every million output tokens, a variable expense that compounds rapidly in automated document processing or agentic workflows. The financial drain is paired with a mounting legal challenge. Transmitting sensitive customer data, from patient records to legal contracts, across public network boundaries introduces massive compliance risks under frameworks like HIPAA and the EU AI Act. However, a shift in edge computing hardware is beginning to alter these economics. The computational density once reserved for remote data centers is now migrating into localized AI PCs and dedicated desktop workstations. As these recurring Telgen fees and data exposure risks aggregate across a global workforce, the centralized cloud model is increasingly functioning as a financial and regulatory bottleneck. This transition is driven by a new baseline for enterprise silicon, specifically architectures like the NVIDIA RTX Spark Superchip and the Apple M4 Pro and Max platforms. The RTX Spark, for instance, integrates 20 ARM CPU cores and a Blackwell generation GPU with 128 gigabytes of unified memory. To understand why this memory matters, we have to look at how large language models generate text. Every single token generated requires the system to pass the model's entire set of active weights through its memory. This makes token generation inherently memory bandwidth bound, rather than compute bound. Unified memory architecture bypasses traditional PCI Express bottlenecks. Instead of separate CPU and GPU pools, both processors share a single memory space. This physical rearrangement allows local machines to process massive models interactively, reducing latency and per-token cost to near zero. The cloud's lack of persistent state makes iterative development workflows prohibitively expensive. Every time an agent attempts to write, compile, and debug code, it must resend the entire conversation history back to the cloud, multiplying token consumption with every recursive step. Moving these debugging cycles to localized hardware enables what's known as agentic iteration. Developers can execute unlimited code generation and validation loops entirely on-premise, paying only the final verified codebase to the cloud, if they send it at all. Eliminating the financial barrier of per-token charges enables the personal computer to function as an active, autonomous collaborator. For tasks involving extreme reasoning complexity that exceed the capabilities of localized silicon, the orchestrator routes the request to a premium cloud endpoint. Before any data leaves the physical device, it is intercepted by a local sanitization proxy. This system acts as a gatekeeper for all outbound payloads. This proxy automatically identifies personally identifiable information, such as names, phone numbers, or enterprise IDs, and masks them with secure placeholders. Only the dense, anonymized business intent is forwarded to the cloud, ensuring that proprietary or sensitive data never crosses the network boundary. This architecture reserves expensive cloud budgets for high-complexity reasoning, while maintaining absolute data sovereignty for routine operations. Performance benchmarks show the result. Local machines can now process large enterprise models at speeds that allow for real-time, interactive use. This hardware development gives enterprises the capability to handle memory-heavy generative tasks on-premise, bypassing the external fees associated with cloud processing. We can manage these workloads through a triage protocol. As seen here, a central node analyzes incoming data blocks. It routes standard tasks downward to local hardware, reserving the expensive cloud connection only for the most cognitively demanding queries. This is effective for high-volume data processing. Local vision models can parse thousands of scanned invoices or transcripts, converting them into structured JSON and stripping away filler words before any information is sent to the cloud. The strategy also applies to agentic coding loops. A complex request is broken into smaller subtasks locally. The machine can then loop through debugging and execution cycles for free, sending only the final, verified code to the cloud if needed. These models can also perform skill synthesis. By connecting to local command line tools, they can automate repository management and draft pull requests without relying on third-party cloud integrations. Local hardware also serves as a privacy gatekeeper. Sensitive information, including names and internal IDs, is masked locally using a sanitization proxy before any data packet leaves the internal network. This triage strategy moves local hardware from a testing environment into a production role, reducing the reliance on variable API spending. But what happens when an enterprise task requires more memory than a single workstation can provide? This diagram illustrates remote direct memory access, or RDMA, over Thunderbolt. It allows a data packet to move directly from the memory of one node to another. By bypassing the standard software stack, the systems can communicate with microsecond latency. Using specialized orchestration tools, organizations can partition a single large model across several machines. The direct physical connection ensures that the model operates as if it were on one large processor. For maximum efficiency, teams use a fully connected mesh topology. In this setup, every machine is wired directly to every other machine in the cluster, ensuring the fastest possible data transfer across the entire group. By removing the network bottleneck, these clusters function as a single on-premise supercomputer, capable of running 100 billion parameter models at interactive speeds. This chart compares the one-time capital expenditure of a local cluster against the recurring costs of cloud APIs. While the initial investment is higher, the flat line of hardware costs is eventually intersected by the rising climb of API fees, often within 6 to 9 months. There is also a regulatory incentive. Compliance with data laws like HIPAA or GDPR is simplified when sensitive information never leaves the local network, avoiding the need for complex external data agreements. A one-time hardware investment can stabilize a budget by replacing unpredictable variable costs with a fixed, owned asset. Shifting workloads locally is not a total exit from the cloud. Frontier reasoning and massive burst capacity still reside on remote supercomputers. Instead, this model represents a hybrid architecture. Edge hardware serves as the primary processing layer, while the public cloud is used as a strategic point of escalation. The key management decision is no longer just whether to use AI, but identifying which parts of your data pipeline stays local. Mastering this triage strategy gives an organization more control over its sensitive data and its long-term operational costs.